Okay, let's continue with our lecture from Monday on continental rifts and passive margins. At the end of the lecture, we were getting into pure shear and simple shear rifts. We talked about how strain was distributed across a rift at depth. That what we see at the surface is just the brittle deformation, except when we talk about core complexes. And to get to talk about core complexes, we introduced the idea of the listric fault there. We talked about these narrow rifts and wide rifts, and then the core complex model. And this has got to do with the extremely high temperature and low strength of this lithosphere. And we talked about where these core complexes were in the basin and range province and what they look like sort of in the large scale. This is several kilometers across, all kinds of interesting fabrics in there. And then we watched this video, and that's where we left at the end of the talk on Monday. So with the permission of my dog, we'll move on to exhumation. And exhumation, we know, is digging up a dead body. Here we've got a king, but in geology, we use exhumation as a way of describing the process of bringing deep materials to the Earth's surface. So, and one example of that would be extension leading to core complex formation. This exhumes the lower crust. So here we see some cartoons of how it happens. So up here in the top left, we see these normal faults which flatten with depth into, this is a detachment zone. We could call that a listric fault, except it's ductile, so it's not really a fault. It's kind of a shear zone. And these blocks, as they subside, they rotate and you get this asymmetry. You know, there's the master fault on one side of this basin. And as extension continues, these faults evolve, they get very complicated. Lower crust, as extension continues, begins to rise into this zone of broad extension. And ultimately, you get this exposure of what was originally the lower crust. Very interesting. So here we're seeing it in a slightly different way. There's the one fault sort of flattening with depth, makes a basin as it subsides. And then here we've got this lower crustal material is being zoomed into a core complex. All right, is that?
Well, I'm just wondering why the basal material rises. Is there just less pressure on it, so it won't?
Yes.
Okay.
Yes. So it's weak. Remember, it's weak. So buoyancy will take over. It can flow, and will start to flow upwards.
Okay, so it's hot too at the same time.
Yeah. Yes.
Okay.
And Clint wants to add something to that.
Just that, remember, y'all, if you pull apart these things, you would leave a huge hole in the ground, otherwise known as a vacuum. And remember what nature really doesn't like?
It doesn't like people.
No, it doesn't.
Vacuum. You're right.
Or the Kirby Company.
Yeah. So some. All right, moving on. All right, so here there's a number of ways to show this in the geologist's eye. So here we've got a different view. We're stretching this, and it's maybe there's magma intruding at the same time. That did happen. Remember, there's quite a bit of volcanic activity in the basin and range, and which means there must be magmas at depth. So maybe that's part of what's contributing to this heating and ductile flow. And then it starts, as extension continues, you start to get these normal faults which flatten with depth, right? This, and then we get a core coming up here. Now there's a glaring mistake in this figure. Can anybody see it? Look at the relative motion between the plates in D. Now, do you see it?
I see right movement, but I see lateral faults.
No, this is a cross section, so it's not right lateral or left lateral, but the upper plate is moving to the left and the lower plate is moving to the right, correct?
Right.
That's not what's happening. It's quite the opposite. The upper plate is moving to the right and the lower plate is probably staying fixed relative. You see it? You see, do people see it now? Please let me know if you don't, because this is to be able to look at a figure and go, that's not right. They're wrong. That's sort of a breakthrough moment in a development of a geologist, is to be able to critically look at a complicated figure like this and say, I understand it, or wait a minute, something's funny here. And there's something funny in D, and for that matter, in E as well. But okay, I hope you guys can see the problem up here. Now, one of the things you see is these things, this is what the geologists are going to see if this is happening in real time. The geologists will be walking up here and they'll be looking at this hole in the ground or the sediments that are filling it. Fanglomerate, that's kind of a fun name. It means it's sort of a combination of the word conglomerate and alluvial fan. So these are clastic terrestrial sediments that were deposited in alluvial fans that fill these basins. And as extension continues, we get the core complex that we saw so beautifully. And if you're lucky, you get little blocks of erosional remnants where the upper plate rocks are still exposed, including ones that are where the units are completely rotated as a result of extension on these faults. Very exciting geology. So here we look at another example. Somebody, these are different ways of trying to explain what people are seeing, right? People are seeing this down in Arizona, that what we were looking at, Saguaro National Park, that stuff, that's what you're looking at. The video was talking about this. But over on the side, you'll see these rotated upper crustal blocks. This black layer. Imagine that's a lava flow. So when the geologist is going out and looking at the units, they're seeing these young lava flows that are almost vertical. How is that possible? And then on top of them are all these very interesting clastic sediments. All right, now let's get back to lips. Large igneous provinces, we've talked about that once, but they're often associated with early stages of rifting. So we've already talked about lips as very large accumulations of igneous rocks, more than 100,000 square kilometers, which is approximately the size of Iceland. Generally mafic, sometimes felsic, and placed very quickly. And here we see a couple of lips associated with the East African Rift, our classic narrow rift. The rift is coming through here. This is the Eastern Rift. This is the Western Rift over here. You see there's not as much voluminous igneous activity associated with the Western Rift as there is with the Eastern Rift. So these lips up to 2 kilometers thick of lava, total volume on the order of 1/3 of a million cubic kilometers. And the composition of rift-related igneous rocks, this is not a petrology class, but it's still useful. We will talk about these rocks, these volcanic rocks, and sometimes plutonic rocks, being typically bimodal in silica with basaltic and rhyolite modes. That is, there's an abundance of basaltic rocks with 50% silica and an abundance of rhyolitic rocks with 70% silica and not much in between. The igneous rocks associated with rifts can result from large degrees of melting of the mantle to low degrees of melting of the mantle. And we can distinguish those on a basis of chemical composition that we don't have to get into here. But the large degree melts are called tholeiites. So we describe these volcanic rocks as tholeiitic. And sometimes they're alkalic, which means they have a lot of sodium and potassium and other things. All right, so what is the relation? Why do we get igneous activity associated with rifting? It's because extension allows stenospheric mantle to rise and decompress, and that allows it to melt. So this is a phase diagram. We're plotting pressure, which is a function of depth in the earth. Remember, we talked about lithostatic pressure. So this is lithostatic pressure of about 100 gigapascals is equal to about 300 kilometers deep in the earth, well into the mantle. And here we see in a dashed line a typical geotherm, the temperature structure of the uppermost 350 kilometers or so, right? Zero at the surface, pretty close to, what's that, 1600 degrees at depth. Now, over here, this gray area is the region where melts are generated. The solidus is the PT environment at which melting starts, right? So anything below the solidus is going to be completely solid. Anything above the solidus will be slightly melted. The liquidus over here is the region to the right where everything is melted. So if you can imagine the magma ocean for the Earth was basically at a temperature higher than the liquidus of the silicate minerals. All right, so what happens in a rift? Why do we get melting in the mantle? In most places, like beneath Dallas, the geotherm is well below the solidus, so there's no melting. But if we let this mantle rise towards the surface, decompress along something called an adiabat. It's a thermodynamic construction, which means that heat is neither gained nor lost. If we allow it to rise adiabatically, then without heating it up at all, it will intersect the solidus at some point. And at that point, melting begins. And the more it rises above the solidus, the more melting occurs, right? There's 15% melting, there's 30% melting, there's 60% melting. That's what we think happens beneath rifts. The extension allows the underlying asthenosphere to rise to the surface, decompress, and melt. And those melts rise to the surface to become igneous rocks. Any questions about that? It's a lot, but it's remarkably simple.
I'm surprised you don't have any ternary diagrams you wanted to show us.
Oh, I want to keep students in the class, not make them run away screaming. If you would like me to inflict some ternary diagrams on you, I'd be happy to, but I suspect you don't.
And thank you for not saying it's pretty straightforward.
Let's see if I can make this video happen.
Most of us have a basic understanding of what magma is. Molten rock below the Earth's surface, which becomes lava when it erupts. What is less understood is how this rock becomes molten in the first place. Consider a simple cross-section of the Earth. Most people know that the Earth consists of 3 great layers: the crust, the mantle, and the core. Many people imagine the mantle as an underground molten sea, but in reality, it's just a very hot solid. If neither the crust nor the mantle is molten, then where do the magmas that feed Earth's volcanoes come from? And what does magma generation have to do with plate tectonics? To answer these questions, we need to think deeply. But not too deeply. We need to think about the outermost 200 kilometers of the Earth. This is the only part of the Earth where conditions are right for the mantle to melt. Another way that geoscientists see this outermost 200 kilometers is as crust, lithospheric mantle, and underlying asthenospheric mantle. The lithosphere is rigid and thus can only cool by conduction. This cooling style differs from the asthenosphere, which is able to convect due to being hotter and weaker. Asthenospheric convection brings the great heat of Earth's interior to the base of the lithosphere. With a depth scale in place, note that the lithosphere generally extends to 100 kilometers deep. A pressure scale can also be added, as pressure varies with depth in Earth's interior. Most geoscientists think of pressure in terms of gigapascals. A pascal is the SI unit of pressure and is equal to 1 Newton per square meter. The intense pressures inside the Earth require that we add the giga, or 1 billion, prefix. Finally, a temperature scale can be added, and now we can plot a line that describes how temperature increases with depth and pressure inside the Earth. This line is called the geotherm. The geotherm identifies the expected temperature at a given depth in the Earth based on these pressure, depth, and temperature relations. Notice how the geotherm slope abruptly changes at the lithosphere-asthenosphere boundary? Since heat is transferred by conduction in the lithosphere, there will be widely varying temperatures. Heat is well distributed via convection in the asthenosphere, leading to nearly constant temperatures with increasing depth. The geotherm in the lithosphere is said to be conductive, while the asthenosphere's geotherm is adiabatic. Let's pause and discuss what the term adiabatic means. In thermodynamics, an adiabatic process is one that occurs without transfer of heat between the system and its surroundings. If heat transfer is observed, it's a negligible amount in comparison to the other measured changes in the system. In the context of Earth's geotherm, adiabatic refers to a process in which pressure increases or decreases greatly, but temperature increases or decreases only slightly. Adiabatic temperature gradients are expected for convecting materials like Earth's asthenosphere. In this case, the asthenosphere's temperature remains almost constant with depth, changing only a fraction of a degree per kilometer. This is different from the lithosphere's conductive geotherm, where temperatures change several degrees per kilometer of depth. The slope of this geotherm is a function of lithospheric thickness. If the asthenosphere's geotherm were to extend to surface depths, its temperature would reach 1,400 degrees Celsius. This is called the mantle potential temperature. Such high surface temperatures are not observed due to the lithosphere's presence. The conductive lithosphere acts as an insulating blanket, causing a wide temperature variation between the asthenosphere and the surface. Okay, so how does all of this help us understand how magmas form? The mantle is composed chiefly of peridotite, and partial melting of this material produces basaltic magma. The melting point of peridotite varies with pressure and depth in the Earth, and is represented on this diagram by a line called the solidus. At temperature and pressure conditions to the left of the solidus, peridotite, and thus the mantle, will remain solid. At temperature and pressure conditions to the right of the solidus, peridotite begins to melt. For magma to be generated from the mantle, its geotherm must cross the solidus. However, from past and present volcanic activity, we know that basaltic magmas exist more than just in theory. This means that some special condition must exist that allows the geotherm to cross the solidus, and thus cause partial melting of the mantle. So, what are these conditions, and which are related to plate tectonics? There are 3 situations that enable the solidus to cross the geotherm and allow the mantle to melt. These are interplate mantle plumes, divergent margins, and convergent margins. Let's look at each of these a little more closely. The first way to melt the mantle is by simply making the mantle hotter. This increases the mantle temperature and is most often caused by a mantle plume like that beneath Hawaii. Notice how as the mantle plume rises through the asthenosphere and ponds at the base of the lithosphere, the geotherm is deflected to higher temperatures? When the geotherm crosses the solidus, partial melting starts to occur in the asthenosphere at the depths indicated on the diagram. If this magma escapes to the surface, it will erupt and form a volcano. This basaltic lava on Hawaii was formed when a mantle plume partially melted the underlying mantle. Here's the global distribution of mantle plumes. Note that the other planets like Mars and Venus, which don't have plate tectonics, have mantle plumes. Mantle plumes then are not obviously related to plate tectonics. The second way to partially melt the mantle is by letting the adiabatic temperature gradient of the asthenosphere extend to unusually shallow depths in the Earth. This requires thinning the lithosphere, as in the case of mid-ocean ridges at divergent plate margins. Notice how, as the lithosphere thins, the geotherm changes in response? If the lithosphere thins sufficiently, the geotherm can cross the solidus and partial melting occurs. This lava erupting in the Lau Basin was formed by decreasing pressure on the mantle. Here's the global distribution of divergent margins. This style of melting is associated with plate tectonics. The third way to melt the mantle is by adding water, as in the case of subduction zones at convergent plate margins. Let's look at a simple cross-section of a subduction zone. The plate on the left is subducting beneath the plate on the right. The subducted plate releases water as it gets deeper in the Earth. This water rises and is incorporated into the overlying mantle, lowering its melting temperature. This is represented on the diagram by changing the dry peridotite solidus to a wet peridotite solidus. Wet peridotite melts at much lower temperatures than dry peridotite, allowing a normal geotherm to intersect it. This causes melting in the mantle wedge above the subducted plate. Mount St. Helens is an example of a volcano fed by magma generated in a subduction zone. Here's the global distribution of convergent margins. This style of melting only happens with plate tectonics. Let's recap. Under normal conditions, the mantle is solid and doesn't melt. However, there are 3 great situations where conditions are right for the mantle to melt. Rising mantle plumes heat the mantle, causing the geotherm to cross the solidus. Divergent plate margins allow the asthenospheric mantle to rise to unusually shallow depths, decreasing pressure on the mantle and causing the adiabatic geotherm to cross the solidus. Convergent plate margins introduce water, thus replacing the regular solidus with a wet solidus that naturally crosses the geotherm. Plumes happen on all convecting-like planets, but decompression melting beneath the spreading ridges and flux melting beneath arcs above subduction zones only happen with plate tectonics. We hope you enjoyed this deep dive into the Earth's mantle and how magmas form as a result of plate tectonics and other processes.
Yeah, I'm curious. So it's said that mantle plumes are not considered a mechanism of plate tectonics.
They're not obviously related to plate tectonics because we see them on Venus and Mars, which don't have plate tectonics. Now, you may be confused because we talked about the plume controversy, and that some people argued that hotspots are plate tectonic features. So yes, what is that? Was that your question?
Yeah, pretty much. Yeah, I figured. I mean, it could still be part of plate tectonics, but not necessarily.
Yes. Well, there may be and as so often in science, it may be that both sides are right. You know, that there are some deep mantle plumes which are not plate tectonic related. Hawaii might be a good example. Iceland, perhaps. And there may be other things that generate hotspots that are related to plate tectonics. If you are confused, it's because the science is confused, and there are advocates for both sides, and you are left to pick and choose your evidence.
Yeah, I'm going to be doing more research on that anyway. So
Yeah, that's great.
Hmm.
It's an interesting topic. Okay, so let's go on to the next slide. So here we've got the continental rift sequence we've been talking about, rift initiation. We talked about that, you know, wide rifts, narrow rifts, core complexes. And then we get to seafloor spreading, right? And you can imagine in your mind's eye that igneous activity is increasing over this sequence as the lithosphere thins, and we ultimately get to seafloor spreading, which is a lot of decompression melting underneath the plate boundary. So something that is a takeaway from this lecture is that rifts form where the lithosphere is weakest. For whatever reason, when stress is applied to the lithosphere, that strain is going to be localized wherever it's weakest. So continental rifting requires a horizontal stress that's sufficient to break the lithosphere somewhere. And the horizontal stress that's needed to rupture the lithosphere can be estimated by integrating the lithospheric yield stress. And here we have two curves. We've seen them before. One for a stronger lithosphere where the MOHO temperature is 500 degrees centigrade, and the other a weaker lithosphere where the MOHO temperature is 700 degrees centigrade. And we know that lithospheric strength varies inversely with heat flow. And a few numbers here. If the heat flow is 50 milliwatts per meter square, which is a little bit lower than normal, that requires an order of magnitude more stress than for the same strain at a region where you have 100 milliwatts per meter squared. Okay. And we've talked about the fact that extension can be accomplished in many ways. So it can be accomplished by faulting, especially in the upper part of the lithosphere, by ductile flow in the lower crust, or by dike intrusion, right? Whichever requires the least energy. This is a system that's going to evolve according to whatever's easiest. All right. So what causes rifts? And there are two end-member explanations. One of them is called active rifting, and the other is called passive rifting. And active rifting is that there's a big mantle upwelling, and that causes a divergence in the overriding plate. And those of you that are impressed with the abundance of large igneous provinces associated with early rifts will go, that looks like a mantle plume was responsible. The other way, the passive rift, is the transmission of far field stresses. Something's pulling on the plate related to distant plate motions. And, what might that be? So one of the things that pulls the plates more than anything else that we'll be talking about more in this course is a subduction zone. So subduction zones drive plate motions. And so if a new subduction zone opens up, then the plates around it are going to be subjected to some new stresses that might result in rifting. Any questions about those two great modes of rifting, active versus passive? All right, here we've got a cartoon of a active rift. So you got a mantle plume, and that's causing an updoming and a lot of early volcanism, and then that's going to weaken the lithosphere, and any stresses are going to be concentrated in this zone of weakness. So that's kind of my active rifting cartoon, and this is my passive rifting cartoon. So here we're extending the lithosphere, which allows the asthenosphere to rise, and this is caused by plate stretching for whatever reason somewhere. Now, can you see how a geologist might distinguish between these two examples? Does anybody see what they would look for in the geologic record?
Be the rising of a volcano and a mound versus
Yes.
thinning.
Yes, exactly. So in one case, we could say if there's volcanism before extension, or if there's volcanism and erosion, right? Because this rising dome is going to be eroded, then we might say that looks more like an active rift. And if we don't see that, if if you don't have early erosion and early volcanism, you might say, oh, must be a passive rift. So it's very simple-minded. Obviously, nature is more complicated than that, but it's one way to think about it. All right, so here are a number of major forces that drive continental rifting. So here is, subduction-related forces. Slab pull would cause extension in this region, right? And in addition, which we haven't talked about because we haven't talked about convergent plate margins and subduction zones yet, but we will. There's a thing called slab rollback. Counterintuitive, where in the cartoons you'll have seen before, this seems like it's a zone of intense compression. In fact, this lithosphere is falling at a higher angle than the plate motion, so that this surface moves at T1 from here to T2 here. That pulls the overriding plate, and that's called slab rollback. And that will also exert an extensional stress on the overriding plate. So there's two subduction-related forces that can cause rifts. Then there are mantle tractions above an upwelling mantle plume, where the convection exerts some stress on the lithosphere, causing it to move apart. And then there are lithospheric buoyancy forces. We talked about the way to make crust in particular weaker is to thicken it, because that increases the temperature in the lower parts, and that will make it weaker. And then that will allow flowage away, and you'll get lithospheric, thinning. Okay. So these are, this would be an active style of rifting, and this would be a passive style, and this would be passive too. All right, and we talked about strain localization, both the pure shear model and the simple shear model. And that the nature of the rift styles are controlled by lithospheric strength, regardless of whether it's a passive rift or an active rift. But in general, your active rifts are going to have higher heat flow than your passive rifts. All right, now we need to develop a new way of thinking about this, a little bit of mathematical way of thinking about extension. So we're going to define the stretching factor beta. It's Greek letter beta. And it's a very simple definition. So what we have on the top is an original lithosphere that's got a width of A and a thickness of B. And we're going to stretch it. And it's going to have a new width of A prime and a new thickness of B prime. And we're not adding any lithosphere, any new material to the lithosphere. We're just stretching it. So this stretched lithosphere, we can define this stretching factor, beta, as either A prime over A, right? A prime over A would be something like, looks like it'd be about 2, right? Or B over B prime, B over B prime. They are the same, right? That'd also be about 2. Does everybody see that? Very simple way to describe the amount of extension that occurs. Any questions about that? So beta can range from 1, which is unrifted, to infinity, which is seafloor spreading. Because seafloor spreading, you're not stretching existing lithosphere, you're creating new lithosphere, right? But for most rifts, what people recognize at rifts, where they've worked out the beta, the extension factor, the stretching factor, for most rifts, beta ranges between 1.2 and 2. Does anybody know why we don't have rifts with an extension factor, a beta greater than 2? Anybody want to venture a guess?
Because the surface rocks can't handle it, they'll give way.
And what happens when they give way?
They either brittle or ductile, they break, they snap.
Well, no, only the upper part is going to do that. The lower part would be ductile. So when you say rocks snap, we go back to Clint's comment about nature abhorring a vacuum. What's going to happen?
It caves in.
Caves in. Do we have a big hole in the center of the earth or what?
I guess it would get filled in with anything above it.
Above it or below it?
Well, oh yeah, well, I mean, well, yes, if it got filled in with something below it, it would still have a vacuum somewhere.
No, if the asthenosphere flows in and partially melts because it's decompressing, then we have a new tectonic environment. What do we call that?
Plume, craton
No, this would be seafloor spreading.
spreading. Yeah.
So the fact that we don't have rifts with beta factors greater than about 2 is telling us about the limit to which lithosphere can be extended without seafloor spreading starting. Okay, it's a way to connect rifting with its continuum seafloor spreading. Students get confused between rifting and seafloor spreading. They use them synonymously and they're not, right? When we're rifting, for the most part, we're just stretching existing lithosphere. But when seafloor spreading happens, we're making new lithosphere. That's a key point from this course over and over again. All right, so let's talk about hanging wall versus the footwall in the low angled extensional systems. Here we got the pure shear model, and we've got, the brittle realm up here, and then down here, this is rheologically weak, and so it's just ductile flow. And here we've got the same thing, but it's a simple shear model. So beta, we can talk about beta in both of them, but obviously it's easier to do beta for the pure shear model than it is, here it's a little difficult, right? What is the beta of this region? Kind of a mixture, so when we're talking about beta, we like to simplify it in our mind's eye. So we're talking about the pure shear model, but it doesn't matter. Still useful. Okay, so one of the things that happens with rifting is the margins of the rift rise. Now, so here we're seeing the Rio Grande Rift, Colorado, New Mexico, El Paso, Texas, a number of basins in here, right? We talked about the fact that rifts are subdivided into different basins with different geometries. There's Albuquerque, and if you go to Albuquerque and look back, you'll see the Sandia Mountains. And here you can see spectacular geology. This is the 1.6, 1.7 billion year old rocks of the Precambrian crust. And sitting on top, I think those are either Mississippian or Pennsylvanian limestones. So this was down at sea level 300 million years ago, and it has risen spectacularly more recently as a result of tectonics, a rift flank uplift on the sides of the Rio Grande Rift. So let's talk a little bit more about the geometry of basins within a rift. Here we're looking at a cross section. Here we're looking at a map view of the same thing, right? A prime on both of them. So we've got here, a rift with an extensional basin. It's kind of asymmetric. This scarp is a normal fault. We're not showing it, but it would correspond to something like this or this. And here we're looking down on it, and we're seeing this master fault, which is controlling this scarp, and the sedimentary basin associated with it. A little bit of uplift on this side, not very much, just a flexural response to this extension. The big uplift is right next to this master fault. Yes, Clint.
Just to point out, the upper diagram is cross section, lower is map view or plan view.
Correct. Thank you.
Otherwise, you might think like, what's that magma body?
Yeah. Yes, thank you for pointing that out. Yeah, it is always good to take a moment and get yourself oriented with any figure. This is an A and a B, so thank you for pointing that out. Now, I want to draw your attention to the radius of curvature of this thing. This is kind of a flexure of the lithosphere. It's a lithospheric response to what's happening. And we can use this curve to estimate what we call the elastic lithosphere. Remember, we talked about the multiple definitions of lithosphere, one of them being the thickness that has mechanical strength. That's the elastic lithosphere. And what we see is that strong plates that have thick elastic lithosphere, they have long, wide basins, whereas weak plates have short, narrow basins and tight curvatures, right? So this elastic thickness of the lithosphere controls rift geometry, especially early during evolution. We're going to talk about two phases in the evolution of a rift. One of them is what happens when there's active extension going on, and the other is what happens later after the lithosphere begins to cool and heal.
So between strong and weak, as far as wide basins, narrow basins, what would be the general distance to consider it wide versus narrow?
That's a good question, and I don't have a good answer for you. That would be an interesting topic for someone to research. Thank you for bringing up that. That's a good point. All right, so we're talking about, remind you about elastic or mechanical lithosphere, what we use to do this, calculate this T sub E. So the thickness of the elastic or mechanical lithosphere could be determined by how the plate bends when loaded, such as outboard from trenches, right? There's the plate is going down, so it has to bend. Around oceanic volcanoes like Hawaii, where you're putting a load on the lithosphere, a big pile of volcanic rocks, or when a load is removed, such as, let's say we had an ice sheet on top of Scandinavia a few thousand years ago, and we've removed all of that, and the lithosphere is going to relax. Now, the base of the mechanical lithosphere is about this is approximated by the 600-degree centigrade isotherm, which is about 50% of the thickness of the thermal lithosphere. Okay. At temperatures higher than 600 degrees, rocks lose strength. At temperatures lower than that, they still have significant strength. So we can think about the, the thickness of the elastic lithosphere using these kinds of representations, right? So here, it's actually this, in this profile, this is complicated because of this low zone of lower weakness. So this one's better, but because here we've only got one of these yield strength envelopes. Here we can see that the mechanical lithosphere, the elastic lithosphere, would be about that thick, right, to that point. That all of this below here is not part of the mechanical lithosphere. All right, so the T sub E, the mechanical lithosphere thickness, is low for weak, hot lithosphere, and it's high for strong, cold lithosphere. For example, the mechanical lithosphere for the Basin Range is about 4 kilometers, whereas for East Africa and the Baikal Rift, it's more like 30. That's reflecting the differences in heat flow. All right. So the rift topography reflects the response of the elastic lithosphere to loading and unloading. So normal faulting unloads the lithosphere next to the fault, causing it to rise. So if we look at this, here we've got the upper plate. Here we've got a large fault that's localizing extension under here. And that's sort of releasing some of the weight, because sediments are less dense than crystalline rocks. and you get an isostatic response, which allows the footwall to rise and make the rift flank uplift. Okay. Any questions about that? All right, and we can do some really complicated models. These are geodynamic models of, here's the original model setup, and we're applying extension to this upper plate, and we're using this rheology, and this is a computer model after looks like, let's see, we've got 28 million years and 50 million years. So obviously more time allows the lithosphere to thin more. You get this kind of a structure, the asthenosphere upwelling there. And then we can do some other things. Here we've got no strain weakening, which is when you strain rocks, they get weaker. And here they're not, the model does not include that. Here it does. Okay. So this is how geodynamic modelers using mathematics and fundamental understandings of physics model these processes in 2 dimensions. Interesting field. All right. So these models have been investigated for their effects of rift spacing, rift fault spacing. And so this study said that strong lower crust that is a low geotherm results in many closely spaced, widely distributed faults with small offsets. This is incapable of exhuming lower crust to produce metamorphic core complexes. In contrast, weak lower crust causes extension to focus on fewer faults of larger offset within a narrower zone. The larger offsets allow the upper crust to rotate and exhume lower crust as metamorphic core complexes, consistent with what we've been saying all along. So here's another model. Now they're using 4 layers: upper crust, middle crust, lower crust, the mantle. Here we've got 25 kilometers of extension. Here's 47. Here's 78. Right, and what you can see is the 1,000-degree isotherms close to the asthenosphere lithosphere boundary. As extension proceeds, these isotherms rise, which implies that this is, the geothermal gradient is increasing, and ultimately you end up in something very close to seafloor spreading. And the other thing you'll notice here is that the deformation tends to focus at the center of the rift as extension proceeds, because this is a positive feedback loop where if you weaken the lithosphere, deformation is going to be further concentrated there as time progresses. All right, so seafloor rifting leads to seafloor spreading sometimes. Here we have a very simple cartoon. It doesn't matter whether we started off as active rifting or passive rifting. It doesn't matter if we've got pure shear or simple shear in the rift, because whatever happens, the lithosphere is going to slowly thin and the asthenosphere is going to rise and melt. And ultimately, if extension proceeds enough through time, we will get true seafloor spreading. And that's what we're seeing there. Now, one of the things I want you to draw is here's the rift. Here's the passive margin. And there's another passive margin over here. So in this evolution from rift, passive margin, this is evolving as the potential plate boundary. Here we have a new plate boundary. Here's the passive margin off to the side in the middle of the plate now, because the plate boundary is here. And this is going to subside because this lithosphere is going to heal and it's going to thicken. And we're going to talk about how that happens. Okay, a little bit about what if igneous intrusions are associated with rifting. Here we've got a nice basaltic dike intruding a bunch of sediments. And this is simply to draw your attention to the fact that everything we've been talking about has been just mechanical extension, looking at the rheology of rocks under different temperature conditions. If we add the fact that igneous activity is going to happen, and it's going to intrude dikes to feed volcanoes at the surface, that's going to further weaken the lithosphere in a way that's not accommodated by these stretching models. So just to make the point that rifting requires even less force than if magma is involved. Okay. All right, so here we got magmatic intrusion stress, looking at the lithospheric stress profiles, lithospheric strength profiles for two places. Here, where there's no igneous activity, that might be captured by this lithospheric strength file. And here, where there's a magmatic dike, much, much, much less strength. So this is, wherever the zone of igneous activity is, it's going to lead to enhanced weakening of that region. All right, so extension is easier with dike intrusion. So here we're comparing the yield stress. Yield stress is associated with just stretching, or with magma emplacement. This is clearly a stronger lithosphere than this one. Just to give you another view of that. All right, now this brings us to the next topic, which is passive continental margins. So here we've got, our rift sequence, and here we've got a passive margin. And here's what this region looks like up close. So this is at the join between continental crust and oceanic crust. That's between continental lithosphere and oceanic lithosphere. And we will have evidence of the rift stage preserved in the older sediments. They may be deeply buried. And then on top of that is another pile of sediments that has a very different geometry because it's responding to a very different cause. So here are the passive continental margins. They face the Atlantic. They're around Australia, around Antarctica, around the Arctic. These are regions, very few around the Pacific. These are regions of intense economic interest because of oil and gas. Most of the on-land deposits of oil and gas have been found, but there are tremendous resources in passive continental margins. We know that in Texas because of the Gulf of Mexico. All right, maybe let's watch this one. This is one of my favorites.
Rifting is the process of stretching and thinning of a continental plate, caused when a single plate starts to break apart into two plates. Rifting sometimes evolves into seafloor spreading. Rifts also provide sites where great thicknesses of sediment can be deposited. If rifting evolves to seafloor spreading, great sedimentary basins known as passive continental margins will form between the ruptured continent and the new ocean. Passive continental margins are great places for major seaports and cities and provide favorite destinations for summer vacations. This video explains all of these things and more. Rifting affects the continental lithosphere. Continental lithosphere consists of the continental crust and the uppermost mantle, which together forms the strong outer shell of the Earth, extending to about 100 to 200 kilometers deep. There is both oceanic and continental lithosphere, and these are the plates of plate tectonics. We say that the lithosphere is rigid because when a strong force pushes or pulls on it, the lithosphere will break. The lithosphere rides on hot, weak asthenosphere, and this makes plate tectonics possible. We say that the asthenosphere behaves plastically because when a force is applied, the asthenosphere will flow or convect, similar to boiling water or the rising blobs in a lava lamp, but much more slowly. The process of starting to pull the lithosphere apart is called rifting. As rifting progresses, the lithosphere thins more and more, allowing the underlying asthenosphere to rise and melt to form magmas that rise to the surface and erupt as lava flows. Good examples of continental rifts are found in the East African Rift, the Rhine-Graben of Germany, and the Rio Grande Rift of New Mexico in the United States. Over time, the lithosphere may thin completely, allowing the asthenosphere to reach the surface. When this happens, seafloor spreading begins, and the single plate becomes two smaller plates. This is what happened when the Red Sea formed, separating the African and Arabian plates. Volcanic eruptions are common during the early stages of rifting. As lithospheric extension progresses, the rifted region sinks or subsides. Sediments are also deposited in the subsiding region, so interbedded terrestrial sediments and lava flows are common in early rift deposits. The more the lithosphere is stretched, the more it subsides. Eventually, the surface of the rift lies below sea level, allowing the sea to invade to form a young ocean like the Red Sea. Sometimes the young ocean may be repeatedly blocked from the sea, allowing the seawater to evaporate and leave behind evaporite deposits such as halite and gypsum. Once the lithosphere has thinned completely, seafloor spreading will begin, and the young ocean will widen enough to make it impossible to block seawater from the larger ocean, ending evaporite deposition. Normal marine sediments, such as limestone and shale, are then deposited as an open seaway is established. Thus, in the evolution of a continental rift widening into an ocean, the sequence of terrestrial sediments and lava, overlain by evaporites, overlain by marine sediments, is expected. Once the lithosphere thins completely, allowing the asthenosphere to reach the surface, seafloor spreading begins, breaking the original one plate into two plates. The young ocean progressively widens with time once seafloor spreading begins. At the same time, the two halves of the original rift subside to become passive continental margins. Passive continental margins are not plate boundaries, but are the two separated halves of where the new plate boundary began to form as a continental rift. Passive continental margins mark boundaries between continental and oceanic crust. Passive continental margins lie beneath continental shelves and coastal plains, like those of the eastern United States and around the Gulf of Mexico. Because rivers flow from continental interiors to the sea, passive continental margins accumulate unusually thick deposits of sediments. These exhibit a sequence of terrestrial sediments and lava, overlain by evaporites, overlain by marine sediments. As seafloor spreading continues, the two halves of the rift, now passive continental margins, are increasingly separated with time. An example of this is seen in the passive margins of the eastern United States and northwest Africa, which once were part of a single plate but were separated beginning in Jurassic time. Today, the two halves of the ancient plate are separated by the Atlantic Ocean, which started as a continental rift. Passive continental margins are natural places for seaports, many of which have grown into bustling seaports, like New York City, Houston, London, Bombay, Calcutta, Singapore, Hong Kong, Shanghai. The huge piles of sediment in passive continental margins are also important because they host many deposits of oil and natural gas. We hope this overview of continental rifting young oceans, and passive continental margins, and how these are related has been informative. The next time you enjoy a day at the beach, take a moment to think about the plate tectonic processes that created your vacation spot.
Now, this is another view of what it looks like as we go from the rift into the beginning of seafloor spreading, So we still have a rift margin. And in fact, at this stage, the drainage is going to be away from the rift. It's not going to be towards the rift until later. But as we go, as this ocean widens, we're going to get a different sequence of sediment.
Might be a little bit of off-wall question, but as far as the evaporates, like halite, is this where the salt domes form?
Well, the salt domes are a later response, but the salt was laid down in the case of Texas and the Gulf of Mexico during the Jurassic. It's called the Luan salt, and this got buried under thick sequences of sediment, and it compressed it. Salt, as you know, is very weak. It flows, it makes diapirs and rises to the surface. Some of them are continuing to rise, but most of the domes, the salt domes, are much younger feature than the actual salt they contain.
Gotcha. Okay.
So what we get is the evolution of this passive margin as this region, which was originally the rift, sinks or subsides. And so this sequence, this asymmetric basin sort of evolves like this. Now, because it's deeply buried, what is this transitional crust is a particularly interesting scientific question, right? We have normal continental crust, normal oceanic crust, and in between, underneath the passive margin, is something called transitional crust, right? So here we've got UTD is on the craton, the Gulf of Mexico, the abyssal plain is on oceanic crust, and this region in here is transitional crust. This is the passive margin. Everything basically south and east of Dallas is somehow associated with this transitional crust. Now here's a view across the, Dallas to the Gulf of Mexico. So here we've got the underlying crust, right? The focus here is on the sedimentary section. We talked about the Luan salt being deposited fairly early, and these salt domes that Brad was talking about rising here. We talked a little bit about the Eocene Wilcox, right? So that Wilcox would be maybe this unit here. So you can see this is getting, the sediments are getting younger upwards and towards the ocean, right? Now, here's continental crust, here's oceanic crust. This unlabeled area under here is the transitional crust. Now, the oil companies are not going to be interested in anything down here. The oil window is up in this region in here. They're not going to go any deeper than about that, unless there's reason to. And they might. Of course, the problem is that they're doing their thing and they're not telling anybody about it. So it'd be nice to know what they can see at greater depths than we can see. But so far, this is a very old profile, but it was back when the oil companies were sharing these kinds of things with us. All right, this is a sort of what's called SPEC data from the Gulf of Mexico. This seismic reflection image that's provided here offshore Louisiana. So there's the continental shelf, and then we go over this region with a lot of these structures. I think you can see that the sediments are being deformed around these structures. Anybody know what these structures might be? Anybody got any thoughts?
Bolts.
Somebody that mentioned it.
Yeah.
Salt domes.
Yes,
Yeah.
these are salt. This here is very much a salt dome. Some of these down here, they may be flowing outward as well, But the oil companies are obviously very interested to understand this geometry because of the fact that many of these interfaces, say between a salt dome and the right sedimentary layer, might contain significant accumulations of oil or natural gas, right? So these kinds of profiles, which are available, are of great interest. Now, out here, there's no deformation in the sediments, right? And this is probably oceanic crust here, and this is, Jurassic and younger sediment, almost no deformation. Deformation is all being caused by the rising and flowing salt. Salt tectonics, it's a thing. All right, so back to the question of what is this transitional crust? There are two models. One of them is that this transitional crust is nearly all volcanic. It's kind of all igneous rocks that formed during the early stages of rifting. And this makes up a class of transitional crust beneath passive margins called volcanic rifted margins, VRMs. Now, the other end member is there are places where the transitional crust is just thin continental crust, where for one reason or another, there was no igneous activity during early rifting. And in these regions, we find exhumed upper mantle as serpentinites. So we'll talk about these two examples. I want to draw your attention to a couple of things here. One is SDR. That's short for seaward dipping reflectors. So here you can see these, something is dipping towards the ocean. So that's a seaward dipping reflector. Here we've got a different situation. There's no seaward dipping reflectors. Instead, we've got something called continentward dipping reflectors. These are rotated fault basins. And we have a serpentinite body beneath the margin there. Also beneath a volcanic rifted margin, we have a high velocity zone, right, where we have gabbroic material, which has a high seismic velocity. And we'll talk more about these things. Any questions about these two end member transitional crust, VRMs versus RPMs? All right, so the VRM model comes from offshore Norway. So Norway's is a big oil producing country, and here we're looking at offshore Norway. We're looking at Moho depth. So here, 40 kilometers, that's normal continental crust. 11 kilometers, that's below sea level, and so that's about 8 kilometers. So that's normal oceanic crust, maybe a little thicker. And in between, we can see the Moho gets deeper towards the ocean, so the crust is getting thinner in this direction. Beneath the volcanic rifted margin of Norway, we see a region where there's high velocity, high P wave velocity, lower crust. And here we're showing the thicknesses of that. Out here, it's 0. In here, it's 0. And beneath here, it gets thicker, 1 kilometer, 2 kilometer, 3, 4. Here, there's a region where it's 6, 7, even 8, 9 kilometers thick, this lower crust. And we're going to look at a seismic, a profile AA prime. So here we have it. We won't worry about the gravity anomaly, but this is the reconstruction. This is continental crust velocities I'm sorry, these are densities, not there. Basically, these are velocities, continental crust velocities. And then here is a region with high velocity lower crust, 7.2. That's much higher than we expect for normal lower continental crust. That's the high velocity lower crust, and which lies below this region where there are seaward dipping reflectors identified in the seismic reflection. This is sort of a sketch showing this basically what's going on below the seafloor. These are sediments lying on the crust, And then these are the seaward dipping reflectors. This is a zone of inner seaward dipping reflectors and an outer seaward dipping reflector unit. Now, in contrast, we can look at the Iberian margin and the Labrador margin as examples of a non-volcanic rifted margin. Here we can see the seismic velocity, the sediment. Here we see the rotated continental blocks. Now we can look at the typical profiles across a volcanic rifted margin versus a rifted passive margin. Here we can see this high velocity lower crust beneath the volcanic rifted margin. Here we don't see that. So here we see the magnetics around the Gulf of Mexico. And one of the things we can see is this magnetic high beneath Houston, right? And that is most easily interpreted as reflecting the presence of a large mafic body, which is magnetized and is showing it that way. And these are models that we generated back 15, 16 years ago to show the magnetic anomaly and the gravity anomaly that would result if we put a volcanic rifted margin under there. And I think it's generally agreed that our model is correct. So why do rifts subside? So most passive margin sedimentary sequences are many kilometers thick, and most sediments were deposited in shallow water. So there must have been a lot of subsidence. So the favored model is that subsidence is caused by initial rapid stretching and thinning of the lithosphere. That's called tectonic subsidence, which is followed by slow cooling and thickening of the lithosphere. That's thermal subsidence. So the stretching thins the crust and so increases the bulk density of the lithosphere, causing it to subside by fault-controlled subsidence. And they will continue to subside as a result of continued cooling, which is thermally controlled. So the total subsidence in a rift or a passive margin is the combination of tectonic and thermal subsidence. And it's these two effects that give the rift basins their characteristic steer's head architecture. So let's talk about the development of this concept. So here is the steer's head and horns. So Texas Longhorn. So the horns basically mark represent the later subsidence, the thermal subsidence phase, and the head represents the tectonic subsidence. And in the next profiles, you might go, oh, it doesn't look like a steer, but use your imagination. All right, so the formation of a classic steer's head and horns basin requires two steps. The first is the stretching of the lithosphere, which forms deep, narrow basins. That's the steer's head. And the second is after stretching stops, lithosphere cools and thickens, causing thermal subsidence, which is the steer's horns, the sag basin. So the head is the rift basin, the horns is the sag basin. The initial subsidence to make the rift basin is fast. The substance that makes the sag basin is slower. All right, so here we're going to stretch the lithosphere. We're going to subject it to a certain beta, so the beta of 2. You can see that what we did is took this length and doubled it, took this thickness and halved it. And now we end up with something like this. This is the section from Norway to the Shetland Islands of near Scotland. And so this is the rift in the North Sea rift graben. Does it look like a steer's head to you? Probably not, but the tectonic substance is down here and the steer's horn is a much wider zone. Okay, so we've already gone through that. So here's what it looks like. Before rifting, our temperature profile, there's our conductive profile, there's our adiabatic. After we rift it, that tectonic, that geothermal profile greatly changes, becomes a steeper gradient in the lithosphere. And then it's the mantle part of the lithosphere is going to want to get back to this situation. This was the stable situation. So if the lithosphere total has been thinned from 100 to 50 kilometers, it's slowly going to thicken until it gets back to 100 kilometers, which is what it was stable. But in that process, the amount of buoyant continental crust relative to the amount of dense lithospheric mantle is halved. So the density of this lithospheric profile is going to be much greater than this one, causing it to subside. Now, you remember the seafloor depth curve? You know, basically, this is what happens around a spreading ridge. You basically thicken the lithosphere with time, which causes it to subside. And so we can use this kind of thinking for what's happening beneath the continental rift. So here we've got a number of curves superimposed on initial substance, tectonic substance, for a beta of 1.25, a beta of 1.66, a beta of 2.5, a beta of 5, beta of infinity. So does anybody know what geologic process would be associated with the beta of infinity?
Seafloor spreading?
Yes. So the limit to the subsidence curve is that of a mid-ocean ridge. So here's we've been talking about the half space cooling models, ridges at 2.5 kilometers and then subsiding with time. So this curve is basically what happens if you get rid of all of the crust and have nothing but the seafloor spreading regime. So these curves are more normal for a rift. And as we said, most continental rifts don't have a beta greater than 2. So, but the point is, the more extension you have, the greater the subsidence. There we can plot beta versus total subsidence. So let's look at the North Sea example. It's, this is Norway we were talking about, and then there's England, and this is a Graben system in the North Sea. And this is one of the things that made Norway so rich in oil, and for that matter, England, Great Britain. I mean, Scotland. If Scotland was a independent nation, it would get more of this. But we can, this region has been divided by the different nations. So Norway gets the income from this, England this, Denmark that. I think that is the Netherlands, and maybe this is Belgium. Now, this was a huge thing a couple of decades ago, and since that time, oil production has been declining very progressively. But so here we are. I'm not sure exactly where we were, but it's going down. It's much less of a resource than it was. Although with new technology, one suspects that they might be able to get some more out of it. And here is the model that sort of the idea for the Steerheads Basin. Maybe this looks a little bit more like a steerhead than the previous ones I showed you. This subsidence was worked out, this idea of how subsidence occurs in sedimentary basins was worked out by a very famous tectonics person, Dan McKenzie, to try and understand what was going on in the North Sea province. And this is what he worked out, basically using the ideas that we've been talking about, beta and tectonic subsidence and things like that. But that's where the Steerhead Basin came from. Which sediments were deposited during or before rifting? Which were deposited after rifting? Anybody want to take a shot at that? Anybody got an idea?
Well,
Well-
Jurassic and Triassic would be before, because they're on an angle, and the rest are gotta be,
Yeah.
because they're flat. Cretaceous and more modern stuff is
Yeah. Yes, it's exactly right. The stuff that's relatively flat was deposited after the rifting was over, during the thermal subsidence phase. The stuff that was rotated, it was either formed during the rifting or before, right? Because the rifting occurred in a region of, say, flat-lying sediments. And we can't tell from just looking at the geometry whether those older sediments are deposited during rifting or prior to. But it's easy to tell the ones that were deposited during the thermal subsidence phase. Okay, now flexural backstripping is what people that do that for specialty do to reconstruct the amount of extension. So here we've got the post-rift sediments. You basically just strip off the sediments, mathematically, because they cause additional substance due to loading. And flexural backstripping is a procedure that determines the depth at which the basement would be without loading by water and sediments. And that allows you to determine the stretching factor, the beta. So here we've got the opening of the Davis Straits and the Late Cretaceous. Greenland was part of North America. And then we see at about 80 million years ago. Anybody know what geologic era that was?
Sure,
What's that?
sure, Cretaceous.
Yep. So we're in the late Cretaceous here. And then in the early Cenozoic, this actually has seafloor spreading. Here we see the seafloor spreading anomalies. And this stops spreading, and the extension instead goes to the other side of Greenland, and that's the Mid-Atlantic Ridge over here today.
Why would it have stopped spreading and shifted the other way?
Good question, and I don't have a good answer for you. So this is the way that this region has been reconstructed. Extension with beta. We're looking at seismic velocities here, and these are the rifts and what happened.